Today's session, Dilip and Rishika will walk us through a secure solution for AI model serving using KServe deployed on confidential containers. Over to you, Rishika.
Thank you. Okay, so we really know that the enterprises want to do AI at the core. But what is really hindering these enterprises to adopt the AI amongst many other challenges? One of the challenges, how do we secure our AI assets? That is our model and data, right? So we are going to talk, so myself, Rishika Kedia, I am the product owner for OpenShift on IBM Z and Linux One Systems from IBM, and I have my colleague Dilip. We'll share the insights on how we can secure the AI inferencing using the confidential containers on KServe. So just want to know, do you people understand how confidential containers work, or have you been using KServe when doing some AI inferencing? Anybody in the audience here? Okay. 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 Sure. So this would focus on inferencing though. Yeah. So the agenda looks like this. So we will first understand the need of why we need actually the confidential containers, and then we give a little introduction to what is confidential containers and what is KServe, and then we show this integrated story of how we achieved secure AI inferencing using these confidential containers. And we'll have a quick demo to showcase that use case. Um, so, some of these regulated industries like finance, healthcare, and government agency bodies, they usually have this requirement: how do we secure or protect our customers' data, both from insiders' misuse and outsiders' threats, right? Just implementing robust access controls, strong encryption, data protection measures suffices. When I say insider misuse, I'm also covering the internal system administrator, because they also have access to that data and can tamper with it, even our internal system administrators. So, having this strong, robust control, role-based access control works, or we can augment it with a strong encryption mechanisms and delegate this key management task to an independent security system, which is called as your hardware security module, or the HSM, which manages these keys, and so the admins cannot access this key management system and cannot tamper with your data. And how often should we keep up with this, regulatory standards? There are a lot of regulatory standards that comes in. Every nation has its own regulatory standards. Like we have NIST, we have PCI DSS, and recently this DORA has come in. So how often we need to keep up with these regulatory standards? And how often should I conduct my regular audits? These are some of the questions that come in when you really need to plan your security around your AI workloads. And now that the data is placed in multiple cloud platform, you will need to have that consistent security measures that caters to these needs of various cloud platforms, right? So, and with this confidential computing technology on which this confidential containers is based on, how can I leverage this and integrate into my existing AI stack so that I get end-to-end protection for during my AI, training, deploying, and inferencing. So, taking a look at the attack vectors. Okay, so taking a look at the attack vectors that, in the premises of AI, like in the confidentiality attacks, so I'm just picking up some of these which are important for us to understand, like the confidentiality, integrity, and availability attacks. In confidentiality attacks, the attacker's aim here is to steal your model and your data also. What I mean by models theft is that, your attacker will gain access to your deployed model and run it so repeatedly and extract the parameters, and they'll try to recreate it. Essentially, they're making you lose the intellectual property of your model and also cause a competitive disadvantage in this process. With the data privacy, they are getting access to your training data, and then again, they can tamper with the training data, right? With integrity attacks, they try to manipulate your models, essentially poison your model and your data so that you get biased or incorrect results. Like, they inject malicious training data into your models so that, your model's behavior is also corrupted. With training, with data poisoning, what they try to do is inject a skewed or the tainted data set so that your model's outcomes are also skewed up. With availability, needless to say, this is just like any other applications. They try to overwhelm your AI infrastructure with so much of request that your resources are so consumed that your systems are becoming unresponsive. So these are the different kind of attacks that we have, but today we'll focus on the confidentiality part of that attack. Sorry, I'm getting used to this. It's not working. Okay, so what is that? How should we stop all this, right? I mean, is there a security measure that helps us to, say about that protects the confidentiality of our AI assets, strengthens the, integrity of our AI assets, with ensuring that there is high uptime availability of our models. So what we are trying to do is we're going to implement a zero trust model. Zero trust model focuses, or it assumes that nothing can be trusted, not even a single user, device, service, nothing. I don't trust anybody, right? So we're going to design our framework based on the zero trust model. It starts with constantly validating that only the authenticated and the authorized user is accessing your AI assets. With supply chain, we are constantly validating the integrity of our AI code before and after deployment. Network security, we try to segment and enforce strong encryption measures so that we are trying to avoid any lateral movements in your AI infrastructure. With data protection, we're trying to cover every state of data, right? Like when I say that, when the data is at rest, you're trying to secure your data via encryption. When your data is in transit, you're trying to secure your data with with your secured communication protocol like TLS. Now, this was something which was missed, right? We have not heard so often, but what we are trying to do is when the data is in use, when your data is in memory, right? Dilip has a demo which shows that how your data can be leaked when it is in memory. This is exactly what we're trying to show, that when your data is in runtime, how confidential computing using it kind of provides a secured enclave using the hardware's trusted execution environment. So there's a facility that your hardware is providing, various processors provide that capability. You can leverage that to run your workloads in a trusted environment. So over to Dilip for taking over to the next. He'll explain us how confidential containers will help us in this path.
Thanks, Rishika. Let's understand what is confidential containers. For that, we will have to understand what are the different stages data gets encrypted. Most of us know data gets encrypted at rest and also in transit. Okay, we'll see at data. Okay, we'll see in data at rest what are the different ways we encrypt it. We can encrypt the entire disk, or we can encrypt the file system. And data services like database also provides the encryption at rest, where you can you can encrypt the data, enter database or certain tables or certain fields also. You can use HTTPS, FTP, or other protocols to protect data which are in transit. But main question is, how do we encrypt the data that is in use? This is where confidential computing will come into the picture. Confidential computing, as Rishika mentioned, provides the hardware-based trusted execution environment, which is a secure enclave, where your data is encrypted and other process can't see your data. Only process that want to use the data will use that. Let's continue to the next stage. Okay, sorry. Okay, let us understand in Kubernetes how we achieve the zero trust. Let's take a step back and understand in virtual server how it is achieved. Then we'll move to Kubernetes and how the trust model will change when it moves to Kubernetes. In the virtual server, we will build our own virtual machine image, and then we'll build our own application and the data, and we'll then provision the virtual server, and we'll control the entire cycle of it. Our virtual machine won't be able to access host, or host cannot access our virtual machine by default, right? So application owner controls the data, application, and also guest virtual machine that is running on it. But when it comes to Kubernetes, the workload provider or the data owner will have access and control over only the pod. They don't have control over nodes or underlying cluster or the host they are hosting on. What challenges it implies? We'll understand with the below diagram. We have different personas like IaaS admin, Kubernetes admin, and workload providers. The workload provider will basically own the data and the code. Now, we have to isolate the workload from Kubernetes nodes as well as the IaaS admin. So my workload provider should not access Kubernetes or the underlying host or the nodes. And on the reverse side of it, the Kubernetes admin or IaaS admin should not access my data or the code which my workload providers are providing. These two X is what confidential container will provide us. Let's continue on to the next slide. Let's see what is model server with KServe. So KServe is the inference platform on Kubernetes, which provides you the scaling capabilities with Knative serving and networking capabilities with Istio. These are the other operators which KServe uses to provide you the inference engines. So this supports both transformer, predictive, and generative workloads. It provides the standardized CRDs and APIs for managing the entire life cycle of your inference service. Let's go to the next slide. Let's understand what is confidential containers and how do we integrate model serving with confidential containers. So confidential containers, we have some glossaries we have to understand the confidential containers. First thing is sandbox containers. So what exactly is sandbox containers? It provides you the security by leveraging the lightweight. It creates the lightweight kernels for you, which runs along with your host kernel. By that, it provides the isolation that is required for your application to run and run as its own process. So other process will not inference with it. For example, kata containers, if you have used kata containers is an example of sandbox containers. But what is the challenge here? Anyone can guess? Okay, it only providing the isolation, but there is no encryption guaranteed. Data in use is still be in the plain text and available for the users. We'll see in the demo how it will be done and how we can basically load the memory pages to get the data and code that is acting upon it. And on the confidential containers, it basically runs within the trusted execution environment, a secure enclave where the data and code will be encrypted in the memory. So nobody, even if you get the memory dump, you can't read the data that is going in. Confidential container uses two services. One is attestation agent and attestation service. Attestation agent sits on the sandbox and make the request for attestation to get the keys. We'll see what are these keys and how it help in encrypting the memory. And attestation service is basically a service which verifies my software stack, which is the legitimate software stack, which is requesting this key, and it approves the keys for decrypting the memory. You'll see in action how it goes. Okay, we have, let us with this chart understand how it works in action. We have hardware trusted environment, that is my TE, and then KVM is my virtualization environment, hypervisor. And DevOps engineer will provision the trustee, and configures it. Here we have two components, key broker service and attestation service. As I said, attestation service is basically a service which will help us to verify and attest that the current workload is legitimate workload to access the key. And then we have key broker service, which basically communicates with KMS and get the key based on the attestation results. On the left-hand side, we have confidential virtual machine, which basically provides the virtualization for you and isolations for you. So here we have a few components like confidential data hub, attestation agent, already we have discussed, and Kata agent. Kata agent is basically an agent on your confidential virtual machine, which communicates with your peer pod and your confidential virtual machines. So peer pod is basically you have a pod within the Kubernetes, and for that particular pod, you create a virtual machine. And execution of your model or any workload that you are deploying will happen on that particular virtual machines. Let us see in action how it works. I have deployed my workload pod, a KServe inference service on the confidential virtual machines. And when user deploys it, we will have a serving runtime image stored in the image registry. This image registry image in the image registry has to be signed and encrypted. Most of us, we use Cosign or any other toolkit, DevOps toolkit to sign the images. That has to be loaded into the Kata agent, loaded by the Kata agent into the image management. Why we are doing this? Kata or confidential containers will never trust anything from outside. It has to be stored locally, but it has to verify its legitimacy, whether it is legitimate and image is not tampered. How do we achieve it? We'll see that. We'll request a public key of this image signing from the trustee to verify this image authenticity. So request key will be sent to the API server, and it will be forwarded to the confidential data hub for verification. Confidential data hub will request for the nonce. This nonce will be attached to the current request, and it will be forwarded to the attestation agent for attestation request. But why do we need a nonce here? Any guesses? Okay. Nonce is a cryptographic signature that gets attached to each request, which avoids the replay attacks. What are replay attacks? Replay attacks are basically a malicious insider will basically see your traffic and try to replicate the request you are making. So server will respond to any of your requests. With nonce, it will verify the signature and it will respond only one time. Signature will be valid for only once. And attestation request is made. Attestation service will basically verifies that it is the legitimate workload that is working on particular trusted execution environment, and then it basically provides the evidence. There is a policy engine also. Policy engine basically a allow and deny list written in Rego. It basically checks whether this workload is legitimate to access this request. And after that, it releases the key. That key will be returned back to the image management for image management to verify this image, whether it is legitimate, and the processing starts after that only. Once the deployment is started, storage initializer comes into the picture, which basically loads the model from the model storage, which can be your S3, GCS, or model registry also. But we need to authenticate with model storage. So how do we protect the secret? Because we have to use Kubernetes secrets, correct? If you want to authenticate with any of the model storage, we will be using Kubernetes secrets. But here, the risk is Kubernetes admin can basically, they are base64 encoded. Kubernetes secrets are base64 encoded. So they can be tampered, and they can be stolen also. This is the risk. How do we ensure that these secrets are protected? We are using a confidential data hub guest tool called sealed secrets, which basically encrypts your secrets and stores it into the Kubernetes secrets. Only trustee can release the key for decrypting the secret, and based on that, your workload can decrypt the secret to utilize it. So we'll see in the demo. This is the demo we have prepared. We have a producer and consumer. Producer basically creates the synthetic data, transaction data that will be pushed to Kafka. And from the Kafka, we will be pulling, consumer will be pulling the messages, and that will be preparing the inference request and making the inference request to KServe, which is deployed on confidential containers, and returns the results back to the consumers for further actions. This is the demo. Let's get started with this. Let's see how we have done the application setup. Our application setup is already done. We have deployed consumer, producer, and our model itself. You can see it as a pod. Let's see how the producer is producing the data. If you see the logs, the data is getting generated. And this data will be pushed to the Kafka, and my consumer is pulling the data from here, and it is predicting what is the probability of the fraud. If it is greater than 80%, it classify it as a fraud. Otherwise, it will not classify it as a fraud. So we'll deploy what are the operators we need. We need OpenShift sandbox operator, which basically provides you the isolation, and then trustee operator is needed for encrypting the memories. So I have two virtual machines, T313, which is only deployed as a sandbox, and another we have A3, which we deployed both sandbox containers and trustee operator. Let us deploy the workload and see how it works in action. Have deployed the fraud detection model onto this, and we will see in the sandbox container how it works. So here we have deployed the sandbox container project using sandbox container operator. Here you see we have created, it has created the peer pod. So there is a pod created, and for that we have a virtual machines created. All the processing is happening on virtual machines. So you can see this number 144. This is the ID of the virtual machine instance that got created on the KVM. So this gets created on the fly. Node gets created on the fly. I'm doing verse list, so you can see 144. This is the virtual machine that got created. Like my other nodes, you can see CoCo compute nodes and control nodes. Let's see what happens with this. And I'm basically taking the process ID of it and how process, using the process ID, I can get the memory dump. And with memory dump, I can get the data and code that I have deployed. So I'm picking the process ID there. And then I'll be fetching the G-core dump of it. Yeah, I have taken the G-core dump, which is a memory dump, memory snapshot, you can say. And using strings, I'll iterating over that file and matching the input, which is my input data. I'm matching that, and if you see, it is showing me all my Python files and also the data and code that is acting upon it. If you wait for some more time, you can see my inputs that I have passed for predictions, right? That is also displayed with this. So how do we overcome this is with trustee operator. Trustee operator is needed for attestation and memory encryptions. I've already taken the memory core dump of it. What I'll be doing is, I'll be doing the same operation I did, and here you see my code or data is not visible. Whatever you are seeing is the memory input streams and other things that is outside of my application. Those are the system operations that you are seeing. not the application data or the code. And other part which I missed out is sealed secrets. We'll see how it works in action. What I'll do is I have a sealed secret called sealed key, which is my AWS secret key I'm using to load the model. When I do base64-key -d, what it is doing is it is basically showing me the sealed data. This is the encrypted data. You can't use it to load the model from AWS. This needs to be encrypted to do that. Yeah, that's all. Any questions we have?
The container that we are running, correct?
It is workload is agnostic. What we have done is we have taken KServe as the workload and demonstrated. We can consume inference service of KServe with confidential containers, so it will provide you the data security that is needed for model.
But I can use confidential containers not only with KServe, but
Yeah, it is not
that is
a
possible.
requirement. You can
It's-
use it with
it's
any
agnostic.
application of your choice.
you have taken just KServe to give a demo.
Yes, any data application you're using which are sensitive, you can use.
This is applicable if I run within Kubernetes, technically, correct?
Yes, operators are built for Kubernetes.
And if I run this within a different platform altogether, which is a serverless platform, I can't use this one. It's
Like,
like you have inferencing platform, serverless, modal, you have run pod, etc.
if it is done on virtual machine, that is your requirement, or it is built.
These are outside, these are offerings basically by a different company altogether.
Okay, no, that is
Can't
the
be
case.
done.
We can't do that.
So this sealed secret concept is from Kubernetes, right? Or else is it provided by CoCo?
Sealed secret is basically an operator which provided by Bitnami. That is the independent operator. But here, trustee we are using to encrypt and decrypt. The key which is used for encryption and decryption is there, right? That is available in trustee. This is the independent operator. Sealed secret is an independent operator. You can use with any workloads. But in our context, we use in conjunction with trustee.
Okay, I get it. We actually use the CoCo framework by CNCF.
Okay.
Confidential containers. It's on Kubernetes. So we had a demo earlier. We haven't used the sealed secret. Just wanted to explore to secure the secrets from the side of the administrators. So and then we are getting the data inside the KServe, right? You know, is the data how it's streaming inside? Like, do we have any framework there? Or
We have some init container called storage initializer, which will be responsible for loading the data from your model storage into the KServe, and it will create a volume for you where your model will reside in.
And then where we can store the inferencing, like after the inferencing is done. So we had this problem and we are working on the CoCo, confidential containers.
Okay.
So we got a problem in getting the data and storing the data, inferencing somewhere.
Okay.
So can you touch how I can save the inferencing from the KServe or Kubeflow, any other tool?
Okay. After inferencing, where you have to store the data. Typically, after inferencing, you can store data into any of the downstream application has to consume, right? So you can use Kafka messaging services, and you can basically make it available for downstream application to consume it. But the problem is, if you want to pass it over the network, you can do that also. But here, your question is very specific to confidential containers, how I can use it. Okay, there is a confidential volumes also that is in pipeline. Once we have that in place, we can basically store it on the volumes locally as well.
Thank you.
But
And
that
then,
is in pipeline.
we can also use the encrypted images, right? You use signing of images, Docker images. The same way we can encrypt those images and store the keys in the KBS and then do the attestation and get the keys. This can be possible, right?
But for that you have to enhance your Kata agent. Kata agent is doing it for you.
Yeah, yeah. We can use a tool called Scopio. It's from the CoCo. Yeah.
Okay.
Thank you
Yeah,
so much.
Thanks for that information.
Hey, hi.
Hey.
How about like serving for multi-models, like come to latency wise, how it will serve?
It is the serving runtime like VLLM which inherently serves the multi-models, right?
Okay.
Or you're talking about serving the multiple models.
Yes.
In that case, you can have model mesh, which has the capabilities to serve the multiple models. With KServe, you can serve only single models.
I mean, single model per pod.
Correct. Yes.
How about the large data set? If I want to go for large
in
model,
that,
then
okay, in LLM use cases, right? LLM use cases also can be served through KServe, but with multi-model, if you want to use KServe, then the KServe community has another project called Model Mesh. You have to use that.